So today we're going to study um, the visual sense of motion. It's how motion, what kind of what kind of information gives gives the eye um, the power to detect that things are moving. You can see here, cars are moving back and forth on the opposite lane in one direction, on a close lane to the right. So that type of motion is analyzed by this structure here called MT plus, and it's the most prominent of your visual areas. There's still a few more, but this is the biggest one. And this is located in humans. It's located here. This is the inferior temporal sulcus. There's a valley here going along the temporal lobe, and it's the underside one. On top of it is the medial temporal sulcus. Now, originally this area is identified in the gray owl. And this owl, the owl has its MT plus located up here along the medial temporal sulcus. So way up here, but humans are along the inferior temporal sulcus. So what does this structure do? Well, you can imagine that with it we stand in front of a corner and we look at the street and we say, hey, it's not time to cross yet. What if you are without an LOC? You see the world in sort of jumps, so like static patterns. So you see the objects, but you can't sense that there's any motion in them. You can't tell what direction. If you look at this, except for seeing where they're pointing, you can't tell which direction they're going in. Now, area MT plus has very large receptive fields. So we'll see another structure like FFA that has it sends information to another structure that starts seeing both sides. But itself is contralateral like LOC. But it also sees it is very poor at identifying objects. You can see here that something's moving, and it's probably a car, but you can't tell much else about it. The other thing that it's different is that it's in black and white. Okay, it's lost its ability to sense color because of the projections it gets from the eye. So with only MT plus, this is what you see, this gray thing, not clear what it is. With only the what stream, area LOC, you see what the objects are, but you don't know how they're moving. When you combine the two together, you see what the objects are and its motion and direction. So these two structures talk to each other, the what stream and MT plus. Now, where's the signal from the eye? How does the signal from the eye get to MT plus? You remember that we had these blobs, and around these blobs, the spokes. The spokes gave us the form, the orientation of the simple cells and things like that. And the blobs give us the color. And they did so because of a projection here from the area L, layer 4C to these higher layers. In the case of motion, information again comes from layer 4C, but then it heads up to layer 4B, where it does its magic. And it then sends motion information to other regions. It sends them directly from here, from the visual cortex, to MT, and also indirectly through V2, V3, the pathways we studied last week. So what you saw here was a light producing an action potential. And you could see that these action potentials got to this output neuron all at the same time, and then it fired. And that neuron here is, in a sense, sensing motion. It's also sensing motion in this direction and this particular speed, because only this direction and this particular speed will cause all these action potentials to arrive at this neuron at the same time. Here you can see the light going in the opposite direction, and you can see all these action potentials arriving at different times, and because of that, the neuron doesn't fire, and this neuron, your motion sensing neuron, isn't activated, and there's no sense of motion. Now, how does the brain figure out which way it's moving? Okay, the direction of motion. Here, it would seem that there's lines moving in different directions. Over here, it would appear that it's moving up and down, right, and left and right at the same time. And here too, but at a different angle. And here, it would seem it's moving back and forth horizontally. But without, if we just saw the lines themselves, we'd see that this one is moving horizontally, this one's moving horizontally, and this one's moving horizontally. So the motion of a line that's moving horizontally can appear when all you see is what's inside the circle different. So why is that? Well, the brain really doesn't know, or you can imagine that this receptive field of a neuron that senses motion, and it can't really tell where the ends of the lines are. So it makes it a best guess that the line is moving perpendicular to itself. So you have all these choices of direction, and it picks the one that's perpendicular. Sometimes. We'll see later what those sometimes are. So that one good guess is that you have these simple cells all tuned to a line moving, each one at this angle, and when you combine them all, you get that sense of motion, this direction, and this angle. But then you get this thing. Here, it looks like the line's moving up, down, then right, and then left. Where in fact, it's just moving back and forth horizontally. So it seems like, and its direction isn't changing at all. But it's down here or it's up here. So the brain must be making some other guesses as well. Like if before we were looking through a round hole, now we're looking through an L-shaped hole. So when it's got an L-shaped hole, it has to, again, guess where the ends of the lines are. And it assumes that the ends of the lines are, as you see over here. Well, we're over, yeah, there and there. So it guesses, it puts the ends where they meet the black over black square. So here it sees the real ends of the lines, and of course, then it gets its real motion. Here it assumes that the lines are, like you see here, perpendicular to the direction of motion. And over here, it again figures out the ends of the line are where it meets the object. So there's a lot of guessing to be done to figure out how a line is moving. Now, what does MT or V1 be the place where you sense motion? Okay, you go to wonder, where do you sense color? Where do you sense different sensations? Well, how do you figure out whether V1, we know, lights up for motion? We have complex cells that do so. So we know that structure gets activated for motion, but does it actually sense motion? So we'll do an experiment here. We're going to, we have these lines moving in different directions, and we're recording first from V1, and then we'll move over here to MT. So we provide a stimulus in different directions. Now it's horizontally. Now it's moving down to the right. And now it's moving up to the right. So you see that this cell prefers this direction of motion. Different cells, different directions. Now we'll move the electrode over to MT plus and see what directions it senses. It doesn't sense this. It doesn't sense this. It, by luck, fires for exactly the same direction of motion. Okay. So both structures fire for that direction, and so we haven't solved the problem. We haven't figured out whether it's V1 or MT that senses motion. We're going to try something else. We're going to try a different stimulus. Here you can see lines moving what seems to be up to the right, okay? And here we'll see lines moving down to the right. Now what we're going to do is take the two and combine them. Okay? We have the same lines we saw before. So on the eye, there's only lines moving down to the right and up to the right. Yet, I think most of you will sense motion just to the right with this stimulus. Okay? So now let's try to do the same experiment as we did before and see if we can figure out what happens. We record from the same two cells for this, what's called, I'm not sure if I'm pronouncing it right, played stimulus. So when the lines are moving in this direction, we know that there's a real line moving down here and a real line moving up this way. But what we perceive is this way. So nothing's happening in MT, okay? But this cell that's sensing down to the right in V1 is firing. Okay? If we change directions, to this direction now, we've flipped around. This is stopped firing. This is started firing. Why is that? Well, because now we perceive movement down to the right. And this is what this one was sensitive to. Okay? This neuron is sensitive down to the right, as is this neuron. But now we have the perception of something moving in this direction, when physically there isn't. Okay? So this one's silent because physically there is no movement on the eye in that direction, in its direction of sensitivity. Yes? I can't say, sorry, I couldn't quiet it down. Repeat your question. Again, I'm having trouble hearing. Yeah. I think it's an important question. Yeah. We'll see if we quiet this down. Okay, because in this grid, so in V1, it's sensitive to motion down to the right, okay? But with this stimulus, there is no motion going down to the right. There's only lines going in this direction and in this direction. One set of lines is moving down, and the other set of lines is moving this way. And so it isn't being stimulated by that. Even though it seems like you see it, it isn't there on the eye. Okay. Thank you for your question. So the other thing is these neurons are sensitive to is attention. Attention is very important. And you can see that this cell is sensitive to movement in the upward direction. Okay? And the dot is moving down. It has a very low firing rate. When it moves up, it has a much higher firing rate. What happens when we have two little dots and they move in opposite directions, but we ask people to switch where they're looking? So in this case, we're following the blue dot, and it's sensitive to up, and so it's firing. Now we put our attention to the green dot. It's moving up, and it started firing. But the blue dot is now moving down. So and now it's moving up, okay? But now it's quiet. So the blue dot, your attention was focused on the blue dot before, and its motion was irrelevant. Okay? So the important thing here is that you have an object moving in the direction that the neuron is sensitive to, but also you need attention. You need to attend to that stimulus for it to fire. You need both the motion and the attention to activate the neuron. Now, MT, like every other structure in the cortex, has columns. Okay, these are different columns of MT. Each one of these columns, for example, this gray area, is in turn subdivided into tiny little mini columns. Mini columns. And within those mini columns, you've got cells that are sensitive to motion of different speeds, but also particular directions. Okay? Like this one's in the forward direction, another one might be in the backwards direction. Then the other thing that these lines are they're of different colors. So the structure is also, when people ask, is sensitive to distance. So the cells that are sensitive to far distances fire in this direction are light up this mini column. Cells of going in this direction and at this distance will fire this column. Now, MT in turn sends its information to two other structures. They're called MSTL for lateral and MSTB for dorsal. And each one analyzes a very different type of motion. MSTL senses an object moving. Okay, so if you're watching this plane go by, or if you're watching a tennis ball go by, any object, the tennis racket itself, any object that's moving. On the other hand, also MSTL is sensitive to eye movement, or produces an eye movement called a pursued eye movement. This one is to simulate a pursued eye movement. You simply ask your eyes to track your own moving finger, and when you do that, your eyes pursue that finger. It's a smooth movement that pursues whatever object is there, tennis ball, your finger. On the other hand, MSTB senses not objects, but you. Where are you going? Which direction are you moving? Here you can see it has a pattern of movement. This is one arrow of many little patterns that are moving on the eye. And that pattern indicates to the brain that you're moving forward, because this is moving backwards, and also you're moving in this direction. So you'll see that there are cells that sense every direction, and therefore sense which way you're moving. So this is called optic flow, and it has a very powerful sensation of motion. You can sense it yourself when you're standing, let's say, or when you're in your car and a car beside you starts moving. sometimes you sense that you're moving. If you're in a subway car and the subway car across from you starts to move, you sense you're moving. Okay? It is though it's that the stimulus of those particular patterns that give you that sensation, and you can see that the different patterns are like there's things moving in this direction when you're moving in the opposite, uh, things moving in this direction when moving, patterns moving forward, they expand, patterns moving backwards, they contract. If you tilt your head in one direction, it goes this way. If you tilt your head in the other direction, it goes this way. You can imagine that there's millions of patterns that that the eye can sense. So different combinations of these, and so you have columns in MSTD, and within each one, you have cells that prefer that particular pattern. The other thing you can see here, that in order to determine that it's this pattern, it's a good idea to get information from the entire eye. So that's the left visual field and the right visual field. And so that's similar then to uh, uh, the fusiform face area, where it gets information from the right and the left visual field. Now, the other thing that these areas can do is something called motion parallax. We saw we had these binocular cells that sense disparity and therefore could give you stereo vision. But that's only good for a certain distance. You can see that the angle between the two eyes gets smaller and smaller with the distance away from you. And so at some point it becomes too small for it to measure. So it needs some other cue to help you measure it. And that other cue is relative motion of objects on the eye. And you can see here two objects, a square and a circle. And you can see an eyeball. And in the eyeball, there's a little yellow line here. And that yellow line represents where the fovea is. So you can see that basically the eye is pointing, well, it's supposed to be pointing straight out all the time. And your head's basically moving back and forth, forward and backwards, forward and backwards. And when it moves, of course, or when you move, then your vision of these objects moves on the eye. And you can see here that the closest object, the square, moves at the fastest speed. So things that are close to you move fast, and things that are in distance move very slowly. You can imagine yourself sitting in a car and looking out the side window. The foreground, the size of the side of the road and the trees on it, the bushes will be zipping by you. Whereas things in the mountains in the distance will be almost still. Okay? And so you can tell by that relative motion that one thing is moving faster than the other, that object must be closer to you, or that object is farther from you. So remember that the ventral stream, uh, the objects themselves are coded in the ventral stream, but this motion system provides a depth attribute to it. I don't know if you watched chipmunks before they leap. They bob their heads up and down, and basically they're doing this. They're trying to figure out how far away these objects are that you might want to jump to, because head motion will do this. Now, another problem happens when you look at one of the objects. So when you look at the near object or when you look at the far object. When you look at the objects themselves, and when your eyes are not still in your head, the relative position of the objects changes, or the relative speed of the object changes. Here we have the eye, the fovea pointing at this. You're looking at this square here. And of course, if you're looking at the square here, the square will be always where the yellow line is, where the fovea is, if you're keeping your eye still on that square. And so here we have the near object not moving and the far object moving on the eyeball. And the opposite occurring here. So in order to figure out how far and how near an object is, besides the relative speed of things, we have to know what the eye is doing, whether it's following it, whether it's moving or not. So how do you figure out whether it's moving or not? That's important survival values. Here you can see an object moving. Here the lion moves and the eye is still. Here the lion is still and the eye moves. In both cases, we have movement of a lion on the eyeball. So the eyeball can't tell you which is which. So, like, of course, you can tell who's moving. It's an important evolutionary thing. And Helmholtz, a guy called Helmholtz, about over 100 years ago, he was a physicist and a physician, and he suggested how this problem is solved by the brain. He proposed that movement on the retina is combined with something called an internal sense of motion that he called corollary discharge. And you can see here that again you have your eye and your lion moving. It's the object motion, or the image of the object motion, and that produces a slip of the object on the retinal slip. And here we also have another signal that causes the eye to move, activates the muscles of the eye, and a copy of it being sent to some part of the brain. And Helmholtz had no suggestions as to what that could be. And in that area, the two are compared. And by adding and subtracting these motions, you can figure out what the perceived motion of the object is. And that hopefully is the true motion. So here we have the image slipping on the retina, and it slips to the left. And here we have eye movements producing a motion of the eye to the right. When we compare the two, they subtract out, and we come to the conclusion that the lion is still. So the two signals cancel. If there were no quality discharge in this situation, you would see the same retinal slip, and you would sense that the lion is moving, incorrectly sense that the lion is moving. This quality discharge also works in different, more complicated situations. Let's say rather than the eye moving, or you move yourself, you walk forward or backwards, that does an expansion or contraction of the object on your eye. And but again, this quality discharge can distinguish between the situation where the lion is walking towards you, or you're walking towards a still lion. It's a big difference in situations. Okay, now for some fun. I'd like you all to look at the center of this swirl and stare at it for a while. What did you see? What was that? Yes. It appeared to be coming toward you. Yes, becoming larger. Now try the same thing, and instead of the face here, as soon as it stops, look at your somebody near you. Same effect there. At home, you can try it on your hands, all kinds of objects. So this is called the motion after effect. And the question is, what causes that? One idea is that it might be neural fatigue. Well, in most normal circumstances, neurons do not fatigue. But there is one possibility, and it's called adaptation. We saw it's sort of a general principle that the brain likes to notice changes, not what's constant, like the pressure of your clothes. You're not interested in the pressure of your clothes or being notified what that is. Only when you want to feel them that you have that sensation. So the system adapts, and then it rebounds afterwards. The other possibility is that there's a purpose to it. That purpose is if there's a constant motion, like that circle was. That circle turns constantly. What it's doing, it's drawing cells, recalibrating the cell's perceived motion. Okay, so you can see it's pulling cells that used to measure this velocity now into uh, near neurons that are measuring this velocity. It packs them in closer here, so you have a finer ability to detect motions at the speed that this is turning. And in doing so, you pull less. These become more coarse. And something neat happens in the middle. So here we go again. We start the motion going. And we pull this cell here that was measuring motion slightly in the opposite direction. And now when it stops, it activates this neuron, and you sense motion in that opposite direction. Because it was pulled into this space by that constant motion. Okay, what's interesting about this? Well, you see that lion, a moving lion, every time those dots start to move, and then it disappears when the dots become stationary or dashes. So what's happening here is that information from MT is being transferred to LOC, and that LOC says, okay, these dots are moving, and they're moving in the same direction. And that pattern is the following. And this section, information goes forward, and the object of the lion is recognized. So this is the binding that happens in LOC caused by motion. What's interesting about this? Well, it would seem that there's a white square moving back and forth across the scene here. But in actual fact, there is no white square moving back and forth. There's only a square that appears in front of the circles, or a square that appears in front of the lines. So the square, the object, is being recognized in two different positions by LOC, and it sends this signal that maybe something is moving, gives you this false perception of motion. So MT and LOC cooperate in sharing information. What's interesting about this? So this thing could be a statue turning round and round. This thing is probably not a statue moving, okay? It's probably some human moving. So the brain is doing some amazing things here. It's getting the relative angles between these moving edges, and deciding not only what the object is, that's probably like a human shape, but that the angle between its arms are still, and the angle between its legs are still, relative to the object. So it's done quite a bit. And here, it's sensing from the way those lines are moving on the eye, that the joints, the relative joints are changing. The arms moving back and forth, the feet are moving back and forth. So this is called biological motion. It's the ability of the brain to put together what little tidbits each part of the eye sees, and be able to see whether it's a rigid structure turning or a human-like structure moving forward. And the analysis of this occurs in a structure called the superior temporal sulcus. So we covered the inferior, there's a medial, and there's a superior temporal sulcus. And that area not only does things like look at what the gait is from a few lines, can also very good at lip reading. So it can sense which way your lips are moving. And if you were to be deaf, you could still make out the words from the way the lips move. So we saw that the output of the visual system goes along two streams, a what and a where stream. And it seems possible that this empty area that we looked at here is a third stream. And some people suggest that it should be given the name of a when stream, because it combines what and where with time, an emphasis on time. So this structure is called the when pathway. And that's it. Okay. So we'll meet again next week, and we'll take up more of the wonders of the brain. Thank you very much.